A catalogue of the night sky holds 25 cosmic secrets. This is the new general catalogue, a map to the universe's most astonishing and baffling creations. By the end of this journey, you will have explored a gallery of celestial oddities that challenge everything we think we know about how stars live and die. We will see a nebula shaped like a human skull, a hole in space where nothing exists, and a stellar nursery that looks like a holiday tree. How can a dying star create structures of such perfect symmetry, and what force can punch a void in the fabric of a nebula? Which cosmic mystery do you find the most compelling? Our journey begins with a ghostly visage staring back from the depths of space. This is NGC 2440, a planetary nebula that earned its nickname, the Cosmic Skull, from a haunting Hubble Space Telescope image. In that view, two dark cavities of empty space resemble the hollow eye sockets of a skull, framed by glowing, nebulous gas that forms a ragged, bony jawline. It is a chilling and beautiful reminder that even in death, stars can create art. But this portrait is more than just a cosmic coincidence. It is the final, explosive testament of a star not unlike our own sun. When such a star exhausts its nuclear fuel, it does not go quietly. It swells into a red giant, then violently sheds its outer layers into space. What remains is the star's incredibly hot, dense core, now called a white dwarf. This tiny, Earth-sized ember, blazing at over 200,000 degrees Celsius, bathes the ejected gas in intense ultraviolet radiation. That radiation makes the gas fluoresce, lighting it up like a neon sign. The specific colors tell a chemical story. The blue-green hues come from ionized oxygen, while the red regions glow from hydrogen and nitrogen. This glowing shroud, the nebula itself, is the star's former atmosphere now expanding into the void. Yet the Skull Nebula is not a calm, symmetrical bubble. Its structure is chaotic, with lobes of gas blown in opposite directions at different times. Astronomers see this as evidence of a fitful, violent death. The central white dwarf likely experienced multiple bursts of mass loss, ejecting material in powerful jets that punched through earlier layers of gas, creating that unsettling, asymmetrical shape. So this cosmic skull is not just an eerie face, it is a fossil record of stellar agony, a snapshot of a star's turbulent final breaths that continues to expand and change, a ghost that will slowly fade over tens of thousands of years. From a stellar ghost, we turn to a cosmic door. NGC 1999, the Keyhole Nebula, hangs in the sky not far from the famous Orion Nebula, a lesser-known neighbor with a far greater secret. At first glance, it is a beautiful reflection nebula, its dust and gas illuminated by the brilliant light of a young, hot star embedded within it. The cloud glows with a soft, ethereal blue like moonlight on frost. But at its heart lies a perfect, inky black patch, a keyhole-shaped void of absolute darkness. For decades, astronomers were certain they understood this shadow. They labeled it a Bok globule, an incredibly dense, cold cloud of gas and dust so thick it blocks all light from behind it, a stellar nursery in its own right where new stars might one day be born. It was a textbook example, a dark blot on a bright canvas. Then the Hubble Space Telescope looked closer, using its sharp infrared eye to peer through the cosmic dust. What it saw, or rather what it did not see, sent a shock through the field of astronomy. That dark keyhole was not a dense cloud at all, it was nothing. A truly empty cavity, a hole had been physically punched through the fabric of the nebula itself. The culprit was the very star that lights up the nebula. This young stellar object, named V380 Orionis, is a tempestuous infant. As it formed, it unleashed powerful jets of material like cosmic blowtorches, shooting out from its poles at tremendous speeds. One of these jets, astronomers believe, blasted directly through the surrounding cloud of gas and dust, carving out a vast, empty tunnel and clearing away all the material that once filled that space. The implications are profound. It means that the violent birth of a star does not just gather material, it can also violently excavate it. These stellar jets can fundamentally reshape their nurseries, clearing out cavities that allow light to escape and perhaps even halting the formation of other stars in their immediate vicinity. The Keyhole Nebula is no longer a simple picture of starlight on dust. It is a snapshot of stellar creation as a destructive, sculpting force, a reminder that in the cosmos, even the act of birth can leave a permanent, empty scar. From that empty void carved by a newborn star, we witness a death of astonishing beauty. NGC 6302, the Butterfly Nebula, spreads its wings across space with an elegance that belies its violent origin. This is another planetary nebula, the final exhalation of a dying star, but its form is utterly different from the chaotic skull we saw earlier. Here, symmetry reigns. Two vast, shimmering lobes of gas expand outward in opposite directions, each one a delicate wing of cosmic material stretching over 3 light-years from tip to tip. They glow in vibrant hues of red and blue, a result of different elements fluorescing under the intense radiation from the nebula's hidden heart. That heart holds the key to this spectacle. At the center of the butterfly is one of the hottest stars ever discovered in our galaxy, a white dwarf with a surface temperature screaming past 250,000 degrees Celsius. This stellar ember, smaller than Earth, is so ferociously hot it emits most of its light in the blistering ultraviolet range, the very energy that paints the nebula's wings with light. But the true wonder of the butterfly lies not just in its heat or its shape, but in its chemistry. When astronomers analyzed its composition, they found something that should not exist. Embedded within the swirling gas were crystals of carbonate minerals, the same materials that form seashells, limestone, and chalk here on Earth. For decades, science held that such carbonates could only form in the presence of liquid water, a stable, cool, aqueous environment. Finding them in the scorching, chaotic outflow of a dying star was like discovering a snowflake in a blast furnace. How could these delicate crystals form in a stellar wind screaming outward at over 600,000 miles per hour? The discovery forced a complete rethinking of chemistry in extreme environments. One leading theory suggests that in the dense, dusty shroud immediately surrounding the central star, atoms can momentarily find shelter, allowing them to assemble into these complex mineral grains even amid the turmoil. The Butterfly Nebula, therefore, is more than a pretty picture. It is a cosmic chemistry set operating under laws we are only beginning to understand. It tells us that the universe can craft the building blocks of planets and even life in the most unlikely of places in the searing aftermath of stellar death. The delicate chemistry of a dying star gives way to the raw, sculpting power of stellar birth. NGC 2264 is a holiday masterpiece painted across the void, a region astronomers call the Christmas tree cluster. At its heart is a sparkling congregation of young, hot, blue-white stars, many just a few million years old, arranged by chance perspective into a distinct triangular shape that gleams like a cosmic evergreen. But the true gift of this region lies not just in the glittering lights, but in the shadow they cast. Adjacent to the cluster stands the Cone Nebula, a monstrous, dark pillar of cold gas and dust stretching 7 light-years long. It is a colossal thunderhead of cosmic material, so dense it completely blocks the light from the stars behind it, creating a stark, pointed silhouette against the glowing red hydrogen gas of its backdrop. This is not a static sculpture, it is a dynamic battlefield of creation and destruction. The brilliant, massive stars of the Christmas tree cluster are pouring out fierce ultraviolet radiation and stellar winds, a hurricane of energy that is relentlessly eroding the Cone Nebula pillar. You can see the effects at the pillar's crest, where the radiation has blown away the thinner gas, leaving behind a jagged, textured top that looks like a mountain peak shrouded in fog. This erosive force, however, is also a creative one. As the radiation pressurizes the gas and dust at the edges of the pillar, it triggers shock waves that compress the material within. These dense knots hidden deep inside the dark column can collapse under their own gravity. In these shielded cocoons, new stars are being born. The very process that is destroying the pillar is simultaneously forging the next generation of suns within it. It is a breathtaking cosmic feedback loop where the death of one stellar era through its radiant fury directly midwives the birth of the next. The Cone Nebula is both a nursery and a monument under siege, its form a fleeting snapshot in a million-year story of stellar renewal. That same stellar wind that sculpts the Cone Nebula also paints the final portrait of countless stars, and few portraits are as vivid or as revealing as NGC 3242, the ghost of Jupiter. Through a small telescope, this planetary nebula appears as a bright, bluish disk of light, its size and hue eerily reminiscent of our solar system's largest planet, hence its haunting nickname. But this is no placid giant. It is a dying star's luminous shroud, and its true structure, revealed by the Hubble Space Telescope, tells a story of a turbulent, multi-stage death. At its core blazes the white dwarf, a remnant star so hot it ionizes the surrounding gas. This creates the brilliant inner shell, a blue-green oval glowing fiercely from oxygen. Encircling this is a second, larger shell of red hydrogen, a relic of an earlier, slower expulsion of material. And beyond even that, stretching far into the darkness, lie faint, gossamer halos of gas, almost ghostly echoes of mass lost by the star hundreds of thousands of years before its final, dramatic collapse. These layered shells are like the rings of a cosmic tree, each one marking a distinct episode in the star's long decline. The star did not shed its skin in one smooth motion. It pulsed and shuddered, blowing off its outer layers in fits and starts over vast stretches of time. The final, fastest ejection then slammed into that slower-moving older material, sculpting the sharp inner edges we see today. But the ghost of Jupiter offers more than just a timeline of stellar death. Its chemical composition is a forensic report. By analyzing the light from its glowing gases, astronomers can inventory the elements forged within the star and then scattered into space. They find helium, carbon, nitrogen, and oxygen, the ashes of nuclear fusion. This particular mix is a crucial clue, a chemical signature that matches what we expect from a star almost exactly like our own sun. Studying the ghost of Jupiter, therefore, is like being given a crystal ball to peer into our own solar system's distant future, 5 billion years from now. It shows us the beautiful, complex, and layered structure our sun will one day create, and it confirms that the very elements that make up our planets and life itself will be recycled back into the galaxy from such a luminous grave. This ghost is not just a reminder of an ending. It is a promise of cosmic rebirth written in light and gas. But the quiet chemistry of stellar ghosts is a whisper compared to the cosmic roar of the giants we encounter next. Our journey now takes us far beyond the remains of single stars and into the violent hearts of entire galaxies. We meet two colossal active galaxies, each a titan in its own right, beginning with NGC 5128, better known as Centaurus A. Through an optical telescope, this galaxy presents a truly bizarre spectacle. It looks like a cosmic accident. At its core is a bright, elliptical galaxy, a vast swarm of older, reddish stars. But slicing directly across its middle is a thick, dark, ragged band of dust, as if someone has smeared a black paintbrush across the stellar light. This is not a decorative feature. It is the scar of a cataclysm. Astronomers are certain that Centaurus A is the product of a colossal galactic merger, a slow-motion crash between a giant elliptical galaxy and a smaller, spiral galaxy rich in gas and dust. That dark lane is the shredded remains of the spiral galaxy, now entangled and being consumed by the elliptical giant, yet the visible chaos is only the beginning. Centaurus A is one of the closest and loudest radio galaxies in our sky. From its core, twin jets of superheated plasma, generated by the galaxy's supermassive black hole, blast outward for over 1 million light-years into intergalactic space. These jets, traveling at nearly the speed of light, are funneled and focused by powerful magnetic fields, acting like cosmic particle accelerators of unimaginable scale. They emit vast amounts of energy, not just in radio waves, but across the entire electromagnetic spectrum, making Centaurus a brilliant beacon of violent activity. It is a galaxy caught in the act of a transformative feast, its past written in a dark dust lane and its present screaming across the universe in jets of raw energy. If Centaurus is a product of a past collision, then NGC 1275, known as Perseus A, is a ruler presiding over a present empire. This galaxy sits at the absolute heart of the Perseus cluster, a sprawling metropolis of over 1,000 galaxies bound together by gravity. Perseus A is the dominant central galaxy, a gravitational anchor for the entire cluster, and like Centaurus A, it harbors a monstrously active supermassive black hole in its core. But the activity here takes a different, even more profound form. The space between galaxies in the Perseus cluster is not empty. It is filled with a superheated, thin gas known as the intracluster medium at temperatures of tens of millions of degrees. This gas should cool over time, collapsing into the center of the cluster and forming a frenzy of new stars. Yet, when astronomers look, they see that star formation in the core is strangely suppressed. Something is preventing the gas from cooling. That something is the black hole in Perseus A. It is not silently devouring material. Instead, it is engaged in a delicate cosmic feedback loop. As gas falls toward the black hole, immense energy is released, not just in jets, but in powerful outbursts that ripple through the surrounding hot gas like sound waves in a pond. These are not sound waves as we know them, but pressure waves of truly astronomical scale, with wavelengths spanning tens of thousands of light-years. In 2003, astronomers using the Chandra X-ray Observatory translated these pressure waves into an audible note, a deep B-flat 57 octaves below middle C. It is the deepest note ever detected in the universe, a hum that has been ringing for over 2 billion years. This hum is the key. The energy from these waves heats the surrounding cluster gas, preventing it from cooling and collapsing. It is a self-regulating thermostat where the black hole's own feeding habits pump just enough energy back into its environment to stop its own future feast from growing too cold. The black hole, therefore, is not just a destroyer. In Perseus A, it acts as a stabilizer, controlling the climate of an entire galactic cluster and dictating the fate of countless future stars. The deep hum of a galactic core is a sound born over eons, but the final breaths of single stars can produce structures of breathtaking precision in a cosmic blink. Among these, 2 planetary nebulae stand out as masterpieces of intricate engineering. The first is NGC 6543, the Cat's Eye Nebula. Through a telescope, it appears as a brilliant blue-green elliptical disk with a sharp, cat-like pupil at its center. But when the Hubble Space Telescope stared into that eye, it saw something far more complex. The cat's eye is not a simple shell of gas. It is a series of at least 11 concentric rings, perfect spheres of glowing material nested inside one another like the layers of a cosmic onion. These rings tell a story of remarkable stellar behavior. The central star did not shed its atmosphere in one continuous event. Instead, it appears to have coughed out its outer layers in a series of regular, timed pulses, each separated by roughly 1,500 years. With each pulse, a new shell of gas was ejected, expanding outward until the next pulse sent another shell racing to catch up. The result is this stunning, layered structure, a fossil record of a star's final millennia ticking away with clockwork regularity. What could cause such precise, periodic outbursts remains a puzzle. Some theories point to a companion star, a hidden binary partner whose gravitational tug could trigger these rhythmic expulsions, like a pendulum swinging in the heart of a dying sun. If the cat's eye is a story written in concentric rings, then NGC 7009, the Saturn Nebula, tells its tale with mysterious extensions. Seen through a telescope, this nebula earns its name not from rings, but from two faint, ansi or handle-like protrusions that extend from its main body along a single axis, resembling the rings of Saturn seen edge-on. These are not solid structures, but lobes of extremely hot, low-density gas shooting away from the central star at phenomenal speeds. Their origin is tied to the violent transition at the nebula's heart. The central star here is evolving rapidly, heating up at an extraordinary rate as it sheds its remaining envelope. This process seems to focus intense stellar winds into two narrow, opposing jets like cosmic blowtorches. These jets, traveling at hundreds of thousands of miles per hour, punch through the slower-moving shell of gas that formed earlier in the star's death throes. Where the jets collide with that older material, they create shock waves that heat the gas and make these ansi glow. They are the scars of a stellar tantrum, the visible evidence of focused energy channeled into space. The Saturn Nebula and the cat's eye, side by side, demonstrate that the death of a star is not a single event, but a complex symphony of processes. One star dies in rhythmic pulses, leaving behind concentric echoes. Another dies with focused fury, carving its signature into the void with luminous jets. Both reveal that the final chapter of a star's life is its most artistically complex, transforming simple spheres of gas into legacies of intricate, beautiful physics. These intricate stellar deaths are visible to us only through powerful telescopes, yet some planetary nebulae hide a playful secret for the backyard observer. NGC 6826, the blinking planetary nebula, offers one of the sky's most delightful optical illusions. Through a telescope eyepiece, it appears as a small, fuzzy patch of light, not unlike many others. But look directly at it and it seems to vanish. Shift your gaze slightly to the side using your peripheral vision, and it pops back into view, solid and bright. This eerie blinking is not a property of the nebula itself, but a quirk of human biology. The center of our retina, the fovea, is packed with cone cells perfect for detecting color and fine detail in bright light, but it is relatively poor at detecting faint, diffuse objects in low light. The surrounding rod cells, however, are exquisitely sensitive to dim light and motion. So when you stare directly at this faint nebula, its light falls on the less sensitive central cones and it fades from perception. Averted vision, looking just to the side, projects the nebula's light onto the rod-rich periphery, making it suddenly appear. The nebula itself is a beautiful shell of gas energized by a conspicuously bright central star, but its lasting fame is this intimate conversation between starlight and the human eye. Not far away in the sky lies a nebula whose visual impact comes from sheer perfection of form. NGC 7662, the blue snowball, is a celestial marble of astonishing symmetry. Through a telescope, it presents as a near-perfect, bright disk of intense blue-green light, like a luminous holiday ornament hung in space. That brilliant hue comes primarily from doubly ionized oxygen atoms, atoms that have lost 2 electrons under the fierce ultraviolet glare of the central white dwarf. This gives the nebula a cool, electric glow that is unmistakable. Its shape, however, is the greater mystery. Many planetary nebulae, as we have seen, are bipolar, elliptical, or wildly asymmetrical, shaped by jets, binary companions, or magnetic fields. The blue snowball's remarkable spherical symmetry suggests a far more serene death. Astronomers believe this points to a star that shed its outer layers slowly and evenly, like a steady, gentle wind, without the violent eruptions or strong directional jets that distort the final shape. It presents a vision of stellar death as a calm, symmetrical exhalation, a bubble blown with cosmic patience. Why do some stars die with such violent asymmetry while others expire in perfect spherical harmony? The answer likely lies in the hidden conditions of the star's final millennia, its rotation, its magnetic field, and whether it lived and died alone or with a companion star whose gravitational tug could stir the ejector into complex shapes. The blinking nebula and the blue snowball, one a trick of perception and the other a paragon of form, remind us that the universe communicates through both illusion and ideal geometry, each revealing a different facet of cosmic truth. While some stars expire in serene symmetry, others are born from chaos on a truly galactic scale. Far beyond the quiet deaths of single suns, a spectacular demolition derby is unfolding between two entire galaxies. Catalogued separately as NGC 4038 and NGC 4039, they are known collectively as the antennae galaxies, and they offer a violent, breathtaking preview of our own galaxy's ultimate fate. This is not a distant, abstract event. Through the lens of powerful telescopes, we watch it in real time, a slow-motion crash that began a few 100 million years ago and will continue for hundreds of millions more. The two spiral galaxies, once separate island universes, have now passed through each other, their mutual gravity acting like a colossal tidal force. This force has not simply pulled them together, it has shredded them. Stretching far out into the intergalactic void are two immense, streaming arcs of stars, gas, and dust, the antennae that give the pair their name. These are tidal tails, each over 300,000 light-years long, composed of material ripped from the galaxy's outer regions and flung into space by the gravitational slingshot effect. They are the permanent scars of the collision, a signature of violence written across the cosmos. But the true drama is not in what was torn away, but in what is being compressed. Within the tangled hearts of the two merging galaxies, clouds of hydrogen gas that once drifted peacefully in spiral arms have been violently slammed together. This sudden, immense pressure triggers a firestorm of star birth, a stellar baby boom of unbelievable ferocity. The Hubble Space Telescope's view reveals a landscape of cosmic carnage and creation. Brilliant blue knots, each a cluster of thousands of newborn stars, blaze across the scene. Pinkish-red regions glow from the ultraviolet light of these young stars, ionizing vast clouds of hydrogen, marking stellar nurseries larger than any in our own quiet Milky Way. Amid this frenzy, astronomers have identified over 1,000 of these superstar clusters, dense balls of stars that may one day become globular clusters, the ancient relics that orbit mature galaxies. The collision is essentially forging an entire generation of future galactic archaeology in a single, tumultuous event. This is where the preview hits home. In roughly 4 billion years, our Milky Way galaxy and our nearest large neighbor, the Andromeda Galaxy, are destined to undergo a similar, slow-motion collision. While stars are so far apart that direct stellar impacts will be exceedingly rare, the galactic gas clouds will collide just as they do in the antennae, likely triggering our own epoch of rampant star formation. The familiar pinwheel of the Milky Way will be utterly distorted, its structure lost to a new, blended shape, likely an elliptical galaxy. Watching the antennae, therefore, is like being given a time-lapse of our own deep future. It is a demonstration that galaxies are not static islands, but dynamic beings that grow, collide, and are reborn through violence, seeding the universe with new stars from the wreckage of the old. The violent galactic collisions that forge new stars pale beside the raw, uncontained fury of a single star's self-destruction. Woven across the constellation Cygnus lies the ghost of such an event, a cosmic tapestry so vast it cannot be contained by a single catalog number. We know its fragments as NGC 6960 and NGC 6992, but together they form the Veil Nebula, the shattered remains of a star that died not with a whimper, but with a scream heard across the galaxy. This is not a gentle planetary nebula from a sun-like star. This is a supernova remnant, the aftermath of a cataclysm where a star many times more massive than our Sun exhausted its fuel and collapsed in upon itself before rebounding in a detonation of unimaginable power. That explosion, which occurred between 5 and 10,000 years ago, was so brilliant it would have been visible in Earth's daytime sky for weeks. Today, what remains is a delicate, filamentary web of glowing gas stretching over 100 light-years across, a bubble of devastation still expanding into space at nearly 200,000 miles per hour. The nebula's haunting, lace-like structure is a direct result of physics on a cosmic scale. As the blast wave from the supernova plows outward at supersonic speeds, it slams into the cooler, thinner interstellar gas that once surrounded the dead star. This collision is not a smooth push. It is a turbulent, chaotic process. The shock wave compresses and heats the gas to millions of degrees, while also becoming twisted and rippled by irregularities in the interstellar medium. The result is these intricate, thread-like filaments. Each strand you see is not a solid thread, but a sheet of glowing gas seen edge-on, its complex folds and curls illuminated by the tremendous energy of the collision. The colors are a chemical fingerprint of violence. The predominant reddish hues come from hydrogen, the universe's most basic element, excited to a fever pitch. The striking blue-green regions glow from oxygen atoms that have been stripped of electrons and are now shining in the intense heat. This intricate lace is, in truth, a forensic snapshot of a shockwave frozen in time. But the Veil Nebula is more than a static monument. It is a continuing event. By measuring the precise expansion of these delicate filaments over time, astronomers can perform a remarkable calculation. They can rewind the explosion, tracing the outward motion back to a single point in space and time. This allows them to estimate the original star's mass and, crucially, the staggering amount of energy it released in its final moment. The numbers are beyond human scale. That one star, in a few seconds, likely released more energy than our Sun will emit over its entire 10-billion-year lifetime. The Veil Nebula, therefore, is a cosmic pressure gauge, its continuing expansion allowing us to measure the echo of a detonation that occurred before the pyramids were built. It is a permanent reminder that the elements forged in its heart, the oxygen, silicon, and iron, were blasted into the void, destined to one day become part of new stars, planets, and perhaps even life. We are, in a very real sense, looking at our own distant origins written in fire and filament. The delicate lace of a supernova remnant shows us stellar death on the grandest scale, but the birth of stars can paint the sky with equal artistry. Just a short cosmic hop from the famous Orion Nebula lies a ghostly athlete frozen in mid-stride. This is NGC 1977, the Running Man Nebula. Its name comes not from glowing gas but from shadow. Here, dark clouds of interstellar dust, cold and dense, drift in front of a backdrop of glowing starlight. To the imaginative eye, their arrangement forms a stark silhouette, the unmistakable profile of a human figure leaning forward, arms pumping, caught in an eternal sprint across the heavens. This cosmic Rorschach test is more than just a playful shape. It is a brilliant demonstration of a reflection nebula at work. Unlike the Veil or the Cat's Eye, which glow from their own excited gases, the Running Man does not produce its own light. Instead, it acts like a cosmic fog bank illuminated by the headlights of distant cars. The headlights in this case are three young, incredibly hot, and massive stars known as 42 Orionis. These stellar powerhouses, each many times larger and brighter than our Sun, flood the surrounding space with intense blue-white light. When that light encounters the vast clouds of microscopic dust grains, flecks of carbon and silicate, that permeate this region of space, something beautiful happens. The tiny dust particles scatter the starlight, much like dust in a sunbeam scatters sunlight in a dusty room. And just as in our atmosphere, where shorter blue wavelengths scatter more easily to create a blue sky, the same physics paints the Running Man's nebulosity with a soft, ethereal blue glow. The dark silhouette itself is simply where the dust clouds are so thick and concentrated that they block the light entirely, creating that dramatic, sprinting shadow against the luminous backdrop. This entire scene is a stellar nursery, a quieter neighbor to the more famous Orion Nebula next door. The massive stars illuminating it are themselves only a few million years old, cosmic infants whose fierce radiation is still shaping the dusty cocoon from which they were born. They are blowing cavities in the cloud, compressing other parts of it, and potentially triggering the birth of the next generation of stars within those dark lanes. So the next time you see an image of the Running Man, look beyond the clever silhouette, see it for what it truly is, a vast, dusty maternity ward painted in borrowed starlight, where the drama of stellar birth is casting shadows that fire our imagination and reveal the quiet mechanics of cosmic creation. That same borrowed starlight that paints the Running Man also sets a neighboring cloud ablaze. NGC 2024, the Flame Nebula, lives up to its dramatic name. It appears as a raging cosmic fire, a vast, flickering structure of orange and black that seems to billow like smoke against the stars. But this is one of the sky's most brilliant illusions. The flame you see is not a fire at all. That rich, textured orange glow is not from hot, excited gas. It is starlight specifically, the brilliant blue-white light from the nearby supergiant star Alnitak, the easternmost star in Orion's belt. That intense starlight is being reflected by a massive, cold cloud of interstellar dust, much like the Running Man. The beautiful, complex shapes we interpret as tongues of flame are actually dark, obscuring dust lanes and dense knots of material silhouetted against that bright, reflected backdrop. It is a play of light and shadow on a truly galactic scale, yet within that obscuring dust lies the nebula's true, hidden heart. The flame is not just a passive screen. It is an active stellar nursery, a thick cocoon of gas and dust where gravity is hard at work. Infrared telescopes, which can peer through the dust that blocks visible light, have revealed a bustling cluster of over 800 newborn stars embedded within the nebula's dark folds. This is a stellar kindergarten of immense productivity. The most influential member of this young family is a massive, brilliant star known as Iris 2b. This stellar powerhouse is still shrouded in dust, but it is unleashing a torrent of ultraviolet radiation and fierce stellar winds. This energy is violently interacting with the surrounding cloud, sculpting it and eroding it from the inside out. You can see the evidence in the nebula's structure. The dark lane that seems to divide the flame is actually a dense ridge of dust being compressed and shaped by the radiation pressure from these young stars. The Flame Nebula, therefore, presents a perfect snapshot of a critical moment in a star's life. It shows us the very material that forms stars, the brilliant young stars themselves hidden within it, and the dramatic feedback loop as those newborn stars begin to destroy the nursery that created them. It is a portrait of simultaneous creation and demolition, all framed by an elegant trick of the light. The fiery illusion of the Flame Nebula is a local spectacle, but to witness a stellar furnace of truly terrifying scale, we must journey far beyond our own galaxy. 170,000 light-years away, in a small satellite galaxy called the Large Magellanic Cloud, a cosmic beast sprawls across the sky. This is NGC 2070, the Tarantula Nebula. The name suggests something large and menacing, and the reality does not disappoint. This is the largest, most violent stellar nursery in our entire local group of galaxies. To grasp its immensity, consider this simple, staggering fact. If the Tarantula Nebula were placed at the same distance from Earth as the Orion Nebula, a mere 1,300 light-years away, it would not be a faint smudge in a telescope. It would dominate our night sky. Its glowing filaments would stretch over 30 degrees, covering an area equivalent to 60 full moons side by side. It would be bright enough to cast shadows on the ground, a permanent, lurid glow painting our nights with its light. This is not a nebula, it is a galactic-scale crucible of creation. At the heart of this monster lies the true source of its fury, a superstar cluster known as R136. This is not a gentle gathering of suns. It is a gladiatorial arena of stellar giants, packed with some of the most massive, luminous, and violent stars ever catalogued. The stars in R136 are not like our Sun. They are behemoths, many containing over 100 times the Sun's mass and shining with the brightness of millions of suns combined. Their surface temperatures scream past 50,000 degrees Celsius. The radiation pressure from these monsters is so intense that it does not just illuminate the surrounding gas, it physically attacks it. These stars blast out stellar winds of unimaginable ferocity, streams of charged particles moving at millions of miles per hour. Where these winds slam into the surrounding nebula, they do not gently push, they excavate. They carve out vast cavities and intricate pillars within the tarantula's gas, sculpting the nebula from the inside with pure radiative force. The entire region crackles with this energy, a continuous feedback loop where the act of stellar birth violently reshapes the environment, triggering more collapse in some areas and utter destruction in others. To look at the tarantula is to see star formation not as a gentle process, but as a dominant, shaping, and almost apocalyptic force. It is a preview of what the universe was like in its youth, when galaxies were smaller, gas was more plentiful, and stars were born in these frantic, colossal clusters that defined the evolution of everything around them. The sheer, unbridled violence of the Tarantula Nebula is not unique. Closer to home, within our own Milky Way, another colossal factory churns with the same chaotic energy. NGC 6357, the Lobster Nebula, is a sprawling complex of gas and dust where star formation operates at its most extreme. This is not a serene nursery. It is a battlefield of competing forces, a landscape sculpted by pure radiative fury. The nebula's intricate structure tells the story of this conflict. Vast, hollowed-out bubbles of emptiness stretch across the scene, their walls glowing faintly from the shock of their creation. Towering pillars of dark dust, reminiscent of the Cone Nebula but on a grander scale, stand like defiant mountains against a luminous tide. Snaking through it all are dark lanes and ridges, dense concentrations of material that have so far resisted annihilation. This entire tortured terrain is the work of stellar giants, and at the heart of the Lobster lies their royal court, the star cluster Pisces 24. This compact group is home to some of the most massive stars known in our galaxy. The brightest member, Pisces 24-1, was once thought to be a single star with a staggering mass of over 300 times that of our Sun, a figure that would have shattered theoretical limits. Further observation, however, revealed a truth both more complex and no less astonishing. Pisces 24-1 is not one star, but at least 3 colossal stellar behemoths locked in a tight gravitational dance. Each one is still a monster, individually weighing in at around 100 solar masses. The combined ultraviolet output of these stars is beyond comprehension. Their radiation acts like a cosmic sandblaster, striking the surrounding nebula with unimaginable pressure. Where the radiation and the supersonic stellar winds from these stars meet the cooler nebula material, they do not simply push it aside. They heat it, ionize it, and compress it into those sharp, glowing ridges that outline the cavities. They also erode the denser regions, leaving behind those iconic pillars, within which new stars may be sheltering and forming under the pressure of the very onslaught that is destroying their outer layers. The Lobster Nebula is thus a perfect snapshot of stellar feedback at its most intense. The massive stars of Pisces 24 are both the products of this dense cloud and the agents of its destruction. They carve their names into the nebula with light and wind, creating a spectacular, chaotic monument that demonstrates a fundamental cosmic truth. The birth of the largest stars is always an act of profound violence, reshaping their surroundings long before their own spectacular deaths begin. The sculpting power of stellar radiation can carve shapes that speak directly to our imagination. In the constellation Cassiopeia, a cosmic arcade classic stares out from the void. This is NGC 281, better known as the Pac-Man Nebula, a sprawling cloud of glowing hydrogen gas that bears an uncanny resemblance to the iconic video game character. The likeness is not in the glowing gas itself, but in the shadows. Dark, obscuring lanes of interstellar dust drift across the nebula's bright circular form, creating a distinct wedge-shaped bite that looks exactly like Pac-Man's wide-open mouth. It is a delightful cosmic coincidence, a playful Rorschach test written in light and shadow across 300 light-years of space. But behind that playful silhouette lies a serious stellar workshop. Those dark dust lanes are not merely decorative. They are often dense, cold clouds known as Bok globules, named for astronomer Bart Bok, who studied them. These are among the coldest places in the universe, dense knots of gas and dust so thick they block all background starlight. Within their dark, frigid hearts, gravity is silently at work. The immense pressure from the surrounding cloud can cause these knots to collapse inward. As they collapse, they heat up, and if enough mass gathers, nuclear fusion can ignite at the core, birthing a new star. The Pac-Man Nebula is dotted with these potential stellar embryos, dark spots against the glow where the next generation of suns may be taking shape. Yet the nebula would not glow at all without a brilliant source of energy. That power comes from a young, dazzling star cluster embedded within the nebula, catalogued as IC 1590. This group of hot, massive stars, just a few million years old, acts like a bank of cosmic ultraviolet floodlights. Their intense radiation bombards the surrounding hydrogen gas, stripping electrons from the atoms in a process called ionization. When those electrons eventually recombine with the atoms, they release energy in the form of the characteristic red light we see. The stars are essentially painting the nebula with their own energetic output. But their influence is more than visual. The fierce stellar winds from these young giants are also shaping the nebula, blowing cavities and compressing the gas at its edges, potentially triggering further rounds of star formation in those dense Bok globules. So the Pac-Man Nebula is far more than a cute shape. It is a dynamic ecosystem. We see the dark, dense nurseries of future stars, the brilliant young stars that currently light the scene, and the ongoing feedback between them, a cycle of creation and destruction that has been running for millions of years and will continue long after that familiar shape has been eroded by stellar winds into something entirely new. The playful shapes of cosmic dust give way to a structure forged by pure stellar fury. NGC 6888, the Crescent Nebula, is a delicate, glowing arc of gas that belies the apocalyptic forces that created it. This is not the quiet remnant of a dying sun-like star. This is the work of a stellar predator in its prime, a rare and terrifying class of star known as a Wolf-Rayet star. These are the universe's most massive stars stripped bare, having burned through their nuclear fuel at a frantic, unsustainable pace. The star at the heart of the crescent, known as HD 192163, began its life with a mass perhaps 20 times greater than our Sun. In just a few million years, a blink in cosmic terms, it raced through its hydrogen, then helium, fusing ever heavier elements in its core. This furious burning generated such intense radiation pressure that it literally blew the star's outer hydrogen envelope away into space. What remains is a naked, searing core of helium, carbon, and oxygen, blazing at a surface temperature exceeding 50,000 degrees Celsius. This exposed stellar heart is the Wolf-Rayet star, and it is screaming its existence into the void. It emits a supersonic stellar wind of unimaginable ferocity, a stream of charged particles racing outward at nearly 9 million miles per hour. This is the star's present, a hurricane of matter and energy. But the Crescent Nebula's unique shape is born from a collision with its past. Hundreds of thousands of years earlier, when this star was a more typical red supergiant, it expelled its outer layers in a much slower, denser wind, moving at a comparatively sedate 200,000 miles per hour. That older, slower-moving shell of gas has been drifting outward ever since. Now, the modern Wolf-Rayet wind, moving over 40 times faster, is catching up. It is like a supersonic jet plowing into a dense fog bank. When these two winds collide, the result is not a gentle merger, it is a violent shock wave. The faster wind slams into the slower-moving material, compressing it, heating it to millions of degrees, and making it glow intensely across the electromagnetic spectrum. The visible arc of the crescent is precisely this shock front, the glowing edge where the present is violently sculpting the past. The structure is a complex, layered shell. The inner cavity is filled with the scorching, fast Wolf-Rayet wind. Surrounding that is the dense, glowing wall of shocked material, the nebula we see. And beyond that, the older, cooler red giant wind continues its slower expansion. This makes the Crescent Nebula a cosmic fossil record with two distinct layers, a timeline of the star's evolution written in gas and shock waves. But this phase is tragically brief. A Wolf-Rayet star lives for only a few 100,000 years in this exposed state before its final, inevitable collapse. The crescent, therefore, is a fleeting spectacle. It is the visible sign of a star consuming itself from the inside out, using its own expelled remains as a canvas to paint a portrait of its violent transformation. We are witnessing a stellar metamorphosis in real time, a beautiful and doomed structure that will only last until the star's final, cataclysmic supernova blast wave overtakes it, recycling everything once more into the interstellar medium. That delicate, glowing arc of the Crescent Nebula shows us a shock wave in action, a star violently reshaping its own past. But what if a star could blow a bubble of such perfect symmetry that it seems almost artificial? Drifting through the constellation Cassiopeia, we find exactly that. NGC 7635, the Bubble Nebula, is a cosmic soap bubble of staggering scale and precision. A nearly perfect sphere of glowing gas, 10 light-years across, floats serenely against a backdrop of swirling nebulosity. It looks like a child's toy blown into the heavens, a fragile, luminous orb that defies the chaotic violence of space. Yet this is no gentle exhalation. It is the signature of a stellar hurricane, a wind of unimaginable force. The bubble is not the quiet shroud of a dying star like the planetary nebulae we have seen. It is an emission nebula, a cloud of gas that glows because it is being bombarded by fierce radiation. At the heart of this perfect sphere lies the source of that fury, a massive, blazing star known as SL20575. This star is a monster containing over 40 times the mass of our Sun and burning at a surface temperature exceeding 35,000 degrees Celsius. Such a star lives fast and dies young, and its entire existence is defined by prodigious energy output. It unleashes a stellar wind of charged particles moving at over 4 million miles per hour, a continuous supersonic gale blowing from its surface in all directions. This is where the bubble forms. The space around the star is not empty. It is filled with a cold, dense molecular cloud, a vast region of gas and dust. As the star's relentless wind expands outward, it pushes against this surrounding cloud, sweeping up the material like a cosmic snowplow. The wind compresses the gas at its leading edge, heating it and causing it to glow with a soft blue light, primarily from ionized oxygen. What we see as the bubble's rim is actually this shock front, the boundary where the star's furious wind meets the static resistance of the interstellar medium. The interior of the bubble is a cavern of hot, thin, wind-blown gas, relatively empty compared to the dense wall that defines its edge. But the Bubble Nebula holds a compelling mystery, a detail that disrupts its otherwise perfect geometry. In most Hubble images, the brilliant central star, SL20575, is not centered within its own bubble. It appears noticeably offset, closer to one side of the luminous sphere. How can the star that blew the bubble not be at its heart? The answer lies in the uneven nature of the environment. The molecular cloud into which the bubble expands is not uniform. On one side of the star, the cloud is denser and offers more resistance, slowing the expansion of the shock front. On the opposite side, the cloud is thinner, allowing the wind to push outward more easily and rapidly. The bubble is not expanding into a vacuum, but into a lumpy, textured medium, and so its shape, while spherical in general, is dynamically shifting, with the star naturally drifting toward the area of least resistance. It is a stunning demonstration of real-time astrophysics, a balance between the star's constant isotropic wind and the irregular landscape it is trying to sculpt. This dynamic interaction tells a larger story. The intense ultraviolet radiation from the massive star is also evaporating the surrounding cloud, eroding the very material that defines the bubble's edge. In the dense pillars and structures around the bubble's lower section, we can see this evaporation in action, with globules of gas being boiled away by the stellar glare. Within these dense knots, the radiation and pressure may also be triggering the collapse of new stars, so the bubble nebula is not a static sculpture. It is a snapshot of a brief, beautiful, and destructive phase. The star's wind carves out a temporary cavity, its light illuminates the walls, and its energy simultaneously destroys and potentially seeds new creation in the surrounding cloud. In a few million years, this massive star will exhaust its fuel and explode as a supernova, its blast wave utterly obliterating the delicate bubble it spent its life creating. For now, it remains one of the sky's most perfect examples of a star writing its name on the cosmos, not with a chaotic explosion, but with the steady, focused breath of a stellar giant. But the perfect temporary bubble blown by a single massive star is a local spectacle compared to the sheer, overwhelming grandeur of a nebula that is an entire galaxy in miniature. NGC 3372, the Carina Nebula, is a sprawling cosmic metropolis of gas and dust, one of the largest and brightest star-forming regions visible from Earth. If the Tarantula Nebula is a monstrous stellar factory in a neighboring galaxy, the Carina Nebula is its equally magnificent counterpart within our own Milky Way, a vast, luminous cloud that contains within it every stage of stellar life and death. This is not a single object, but a universe in a bottle, a chaotic, beautiful ecosystem where stars are born, live, and die in spectacular fashion. Its most famous and most terrifying resident is not a gentle giant, but a cosmic time bomb. Eta Carinae is a hypergiant star, one of the most massive and luminous stellar objects known. It contains the equivalent of at least 100 suns, and for a brief period in the 1800s, it became the second brightest star in the entire night sky, not through steady burning, but through a catastrophic tantrum. Between 1837 and 1856, Eta Carinae experienced what astronomers call the Great Eruption. In an event that defied all contemporary understanding of stellar behavior, the star violently expelled an enormous amount of material, roughly 10 times the mass of our Sun, into space. This was not a slow, steady wind. It was a convulsive, explosive outburst. That ejected material did not simply drift away. It formed a spectacular, bipolar structure known as the homunculus nebula. From our perspective, it looks like a glowing, dumbbell-shaped cloud of gas with Eta Carinae blazing at its center. The two lobes are expanding outward at over 1.5 million miles per hour, and they glow not from starlight but from the heat of their own violent creation. The homunculus is essentially the star's own flesh, flung out into space and still warm from the trauma. This event was so extreme that for over a century, astronomers debated whether it was a true supernova that the star somehow survived. We now understand it as a colossal stellar outburst, a preview of the star's inevitable and likely imminent final supernova detonation. Eta Carinae is a star living on borrowed time, and the homunculus is the permanent scar of its last near-death experience. Yet the drama of one unstable star is just a single act in the Carina Nebula's epic. The nebula itself is a tapestry of creation. Towering pillars of cold gas and dust, reminiscent of the iconic pillars of creation in the Eagle Nebula, rise from the glowing cloud. These dark, mountainous structures are stellar nurseries, their dense interiors shielding collapsing cores of gas from the intense radiation that floods the region. That radiation comes from the nebula's many brilliant open star clusters, like Trumpler 14 and Trumpler 16, which contain some of the hottest, most massive O-type stars in the galaxy. These stellar powerhouses flood the nebula with ultraviolet light, sculpting the pillars through erosion and simultaneously triggering the birth of new stars within them by compressing the gas at their edges. The entire scene is a dynamic, self-regulating engine of star formation. Here you can see brilliant blue reflection nebulae where starlight scatters off dust, glowing red emission regions where hydrogen is ionized, and dark, obscuring lanes of cold molecular gas. It is a full-color tutorial in interstellar physics. The Carina Nebula is more than a beautiful deep sky object. It is a living laboratory, a place where we can study the entire life cycle of stars, from their turbulent birth in dark pillars to their stable middle age in glittering clusters, and finally to their explosive deaths as foreshadowed by the unstable fury of Eta Carinae. To observe it is to witness the ongoing story of our galaxy, written in light, shadow, and titanic force. The explosive grandeur of the Carina Nebula showcases stellar life at its most extreme, but the death of a more modest star can produce a farewell of breathtaking intricacy. NGC 3132, the Southern Ring Nebula, hangs in the southern sky like a luminous hourglass, a delicate bubble of gas with a dark central waist. Through a small telescope, it appears as a simple, glowing ring, earning it the nickname the Eight-Burst Nebula for its resemblance to a circular firework. Yet this serene facade hides a complex drama of stellar partnership and sculpted gas. At the heart of this beautiful nebula lies a surprising duality. The primary actor, the star that actually shed its outer layers to create the nebula, is a faint, hot white dwarf. This Earth-sized ember, the remnant core of a sun-like star, is incredibly dim and was only identified with certainty by the Hubble Space Telescope. It is the ghost of the progenitor star, now cooling in silence, but it is not alone. Orbiting nearby is a second, brighter star, a companion that shines with the steady light of a middle-aged sun. This binary partnership is the key to understanding the nebula's remarkable shape. Most planetary nebulae from single stars tend toward spherical symmetry, like the blue snowball. But when a dying star has a companion, the gravitational dance between them can channel the outflow of gas into distinct bipolar lobes. Astronomers believe that as the primary star swelled into a red giant, its outer atmosphere began to spill toward the companion star. This interaction funneled the ejected material into two opposing jets, creating the distinct hourglass shape we see, with a dense ring of gas pinched at the center where the star's gravitational influences met. But the southern ring's complexity does not end with its twin lobes. Hubble's sharp eye revealed concentric shells of gas surrounding the central region, faint echoes of earlier, slower mass lost from the star. These are like tree rings, marking quieter periods of expulsion before the final, dramatic ejection that formed the main rings. Even more striking are the structures at the nebula's outer edges, a series of radial, tadpole-shaped features known as cometary knots. Each knot is a dense globule of gas and dust with a bright, ionized head and a long, trailing tail that streams away from the central stars. They look like a school of cosmic minnows fleeing from a central light. These are not comets, but rather dense remnants of the star's original atmosphere that have survived the nebula's expansion. The intense ultraviolet radiation from the hot white dwarf is slowly evaporating them, sculpting their tails and causing them to glow. Their very existence, arranged in a radial pattern, suggests they were shaped by a final, fast wind from the dying star that swept past slower-moving blobs of material. The Southern Ring Nebula, therefore, is a masterpiece of celestial mechanics. It tells a story of a star that did not die alone. Its faint white dwarf core holds the history of its nuclear life. Its brighter companion star reveals the gravitational choreography that shaped its death shroud, and the cometary knots are the last fragments of its atmosphere, slowly dissolving into the interstellar void. It is a beautiful testament to how stellar partnerships can turn a simple stellar death into an elaborate, structured farewell. From the delicate, structured farewell of a single star, we arrive at a city of suns so ancient it predates our galaxy itself. Our final object, NGC 104, is not a nebula at all, but a glittering, spherical metropolis known as 47 Tucanae. This is a globular cluster, a tightly bound sphere of several 100,000 stars, all held together by their mutual gravity in a space only 120 light-years across. To understand its density, picture this. If you lived on a planet near the cluster's core, your night sky would not be dark. It would blaze with the light of tens of thousands of stars, each as bright as Venus appears from Earth, creating a perpetual, dazzling twilight. This stellar city is unimaginably old. The stars within 47 Tucanae formed over 11 billion years ago, when the universe itself was in its infancy. They are cosmic relics composed almost entirely of hydrogen and helium, with only trace amounts of the heavier elements forged in later stellar generations. Studying them is like reading a history book written in starlight, offering a pristine glimpse into the conditions of the early cosmos before planets like Earth or life itself were even possible. But this ancient city is not a quiet retirement home. Its incredible density creates a dynamic and sometimes violent environment. At its brilliant, blazing core, stars are packed so closely that they can interact, collide, and even swap partners in complex gravitational dances. This has led to a remarkable population of exotic stellar corpses. 47 Tucanae is a known haven for pulsars, the rapidly spinning, city-sized cores of exploded massive stars that beam radiation like cosmic lighthouses. It also contains many X-ray binary systems, where a normal star is locked in a tight orbit with a neutron star or a black hole. In these systems, material is ripped from the living star and spirals onto its dense companion, heating to millions of degrees and emitting powerful X-rays in the process. The presence of these objects tells us that in such dense stellar environments, the life cycles of stars play out in accelerated, dramatic fashion. The cluster is a natural laboratory for studying extreme astrophysics, all contained within a single, shimmering sphere. Globular clusters like 47 Tucanae are more than just beautiful sights. They are the founding blocks of galaxies. Astronomers believe these dense spheres were among the first structures to coalesce from the primordial gas of the early universe. They then gathered, over billions of years, under the pull of gravity to help form the vast halos that surround spiral galaxies like our Milky Way. Each cluster is a time capsule, preserving the chemical and dynamical history of a universe just beginning to organize itself. So as we conclude our journey through 25 strange objects, we end not with an explosion or a delicate nebula, but with a silent, ancient congregation. 47 Tucanae represents a different kind of cosmic mystery. It is not about a single, fleeting event, but about enduring structure. It asks us to consider deep time, to look at a sphere of ancient light and see the foundational seeds from which galaxies and ultimately we ourselves were built. These ancient globular clusters and delicate planetary rings all obey a universal set of physical laws, a cosmic sculptor's toolkit that carves order from chaos. The breathtaking variety of forms we have witnessed, from the perfect sphere of the Bubble Nebula to the intricate hourglass of the Southern Ring, are not random artistic expressions. They are the direct, predictable results of fundamental forces playing out on an unimaginable scale. By understanding just a few key processes, we can begin to read the stories written in gas and starlight. Take the striking bipolar shapes like the Butterfly Nebula or the Saturn Nebula's handle-like extensions. These symmetrical, two-lobed structures almost always point to a hidden engine of focused energy. The secret is often a disk of material and a pair of powerful jets. Imagine a dying star with a close companion, or even a rapidly spinning single star. As it expels its atmosphere, that material doesn't just float away evenly. It can form a dense, spinning disk around the star's equator like a cosmic whirlpool. This disk acts as a barrier, blocking the outward flow of gas in that plane. Meanwhile, from the star's poles, where resistance is lowest, superheated material can blast out in two narrow, opposing jets at nearly the speed of light. These jets act like cosmic blowtorches, punching through the slower-moving cloud and carving out two vast cavities. What we see as two beautiful lobes or ansae are simply the walls of those cavities, illuminated by the star's fierce radiation. It is a stellar death sculpted by its own spin and focused fury. For the immense pillars and evaporating globules like those in the Cone Nebula or the Carina Nebula, a different force takes the lead: radiation pressure. The light from massive stars is not just illumination, it is a physical wind. Photons, the particles of light, carry momentum. When they strike atoms and dust grains in a nebula, they give them a tiny push. From a single star, this push is negligible, but from a cluster of stellar giants like those in the Lobster Nebula, the combined photon pressure is colossal, a gale of pure light. This radiation pressure, combined with the actual stellar wind of particles, slams into the surrounding molecular cloud. It compresses the gas at the cloud's edge, often triggering new star formation. But it also erodes the cloud like ocean waves eating away at a sandstone cliff. The densest, most resilient knots of gas and dust withstand the onslaught longer, left standing as towering pillars while the thinner material around them is blown away. Those dark knots at the pillar tips, the so-called evaporating gaseous globules, are where the radiation is literally boiling away the gas, sometimes revealing a newborn star cowering inside. These structures are not monuments, they are battlescapes showing the relentless force of starlight as a sculptor. And then there are the truly colossal shapes born from gravity's slow, irresistible dance. The majestic tidal tails of the antennae galaxies, stretching for hundreds of thousands of light years, are gravity's signature. When two galaxies pass near each other, their gravitational pull does not act uniformly. The side of one galaxy closer to the other feels a stronger tug than the far side. This difference, a tidal force, stretches and distorts the galaxies, pulling long streamers of stars, gas, and dust out into the void. It is the same force that creates Earth's ocean tides, but scaled up to a cataclysmic galactic level. These tails are not trails of destruction, but ribbons of creation, as the compressed gas within them ignites firestorms of new stars. Similarly, the violent mergers that create galaxies like Centaurus are orchestrated by gravity's relentless pull over billions of years, twisting orderly spirals into chaotic ellipticals and funneling vast rivers of gas onto supermassive black holes. Gravity is the architect of the largest structures in the universe, and its blueprints are written in these distorted, colliding forms. So the next time you see an image of a celestial wonder, look beyond its beauty. See the physics in action. That delicate bubble is a stellar wind meeting interstellar resistance. That dark pillar is a shield against a hurricane of light. Those sweeping tidal tails are the handwriting of gravity on a galactic scale. Each strange shape is a frozen moment in a dynamic equation, a testament to the fact that the universe, in all its apparent chaos, is following a beautifully consistent set of rules. This cosmic artistry remained invisible for most of human history. The New General Catalogue itself began as a simple list of smudges, a 19th-century astronomer's attempt to bring order to the night sky. John Louis Emil Dreyer, working at the Earl of Ross's Observatory in Ireland, compiled observations from many sources into a single, definitive catalogue published in 1888. His goal was not to explain the nebulae, but simply to map their positions with precision, to distinguish permanent celestial objects from transient comets. He could not have known that each numbered entry in his new general catalogue was a gateway to a profound mystery, a story waiting for the right technology to be told. For a century after its publication, astronomers peered at these faint blurs through the lenses of ever larger ground-based telescopes, slowly discerning basic shapes and colors, but always battling the distorting shimmer of Earth's atmosphere. The true revolution, the moment these cosmic smudges snapped into sharp focus as intricate worlds, arrived in April 1990. That is when the Hubble Space Telescope opened its eye to the universe, freed from the atmospheric veil. Hubble did not just take prettier pictures, it transformed our understanding. Its crystal-clear vision revealed the concentric rings of the Cat's Eye Nebula, the delicate shock filaments of the veil, and the evaporating pillars of the cone. It resolved the double star at the heart of the southern ring and pinpointed the white dwarf in the ghost of Jupiter. Each observation turned a fuzzy catalogue entry into a detailed physical puzzle, allowing astronomers to measure motions, analyze chemistries, and test theories of stellar evolution against reality. Hubble showed us that the cosmos is not painted in broad strokes, but in fine, filamentary detail. Now, a new chapter is being written in infrared light. The James Webb Space Telescope sees the universe through a fundamentally different lens, one that peers not just around cosmic dust, but through it. Where Hubble sees a dark pillar like the Cone Nebula as an opaque silhouette, Webb's infrared gaze penetrates the dust, revealing the newborn stars hidden inside their dusty cocoons. It analyzes the chemical fingerprints in nebulae like the tarantula with unprecedented precision, identifying complex molecules frozen on dust grains in stellar nurseries. Webb is looking at the same catalogue numbers, but it is showing us their hidden interiors, their birth chambers, and their coldest, darkest components. This continuous technological journey, from Dreyer's handwritten ledger to Webb's digital infrared mosaics, proves a profound point. The new general catalogue was never an endpoint. It was a starting pistol. It marked the moment humanity decided to catalogue the unknown, initiating a chain of discovery where each new tool does not just provide answers, but peels back a layer to reveal even deeper, more wonderful questions waiting in the dark. Yet these magnificent portraits of cosmic physics are still incomplete. For every law we can trace, a deeper mystery whispers from the dark. The perfect concentric rings of the Cat's Eye Nebula, for instance, present a puzzle of celestial timekeeping. What internal stellar mechanism could trigger such rhythmic, clockwork pulses of mass loss every 1,500 years? A hidden companion star seems a likely conductor for this symphony, its gravitational tug pulling material away in regular intervals. But the precise choreography, the physics of that stable, repeating heartbeat in a star's final chaotic millennia, remains just out of reach. Similarly, the profound influence of a binary partner, as we suspect in the Southern Ring, raises its own compelling question. How exactly does a companion star transform a gentle, spherical exhalation into an elaborate hourglass or a pair of brilliant lobes? We understand the broad strokes gravity channels the flow, but the fine details of that gravitational dance, the way it focuses immense energy into narrow jets that can sculpt light years of gas, is an active frontier of astrophysical modeling. Then there are the monsters. The ultimate fate of a hypergiant like Eta Carinii hangs over the Carina Nebula like a sword. We know it will explode. The great eruption was a terrifying prelude. But when? Will its final supernova be a typical collapse or something entirely new? A pair instability event so violent it leaves nothing behind, not even a black hole. Each strange object we have explored is a single frame in a cosmic film, and we are left to deduce the entire story. The dark globules in the Pac-Man Nebula, will they truly collapse into stars, or will they be evaporated first by the surrounding radiation? The delicate bubble nebula, how will its shape evolve as its central star races toward its own explosive end? These are not just academic curiosities, they are clues in the grandest puzzle of all, understanding the full life cycle of matter, from its birth in the Big Bang to its recycling through generations of stars and nebulae, and ultimately into the building blocks of planets and life. Every bizarre ring, every colliding galaxy, every ghostly skull of gas is a piece of that story, waiting for the next generation of telescopes and the next brilliant insight to help us see the complete picture. From ghostly skulls to galactic collisions, these 25 objects are a testament to the universe's boundless creativity. We have wandered through stellar nurseries lit by newborn giants, stood before the intricate lace of ancient supernova, and witnessed galaxies tearing each other apart in slow motion. Each entry in the new general catalogue, from the serene blue snowball to the tempestuous tarantula, reveals a different chapter in the epic story of matter and energy. They are not just distant points of light, they are answers written in physics, chemistry, and time, yet every answer uncovers a deeper layer of questions. Why do some stars die with perfect symmetry while others explode into chaos? What unseen forces choreograph the delicate rings and jets? The NGC is far more than a dusty old list. It is a living map to the frontiers of our understanding, a catalogue that proves the more we see, the more we have left to wonder. So tonight, step outside. Look up at the stars and remember that hidden within the constellations are these incredible wonders, each with a story waiting to be told. Which of these cosmic oddities captured your imagination the most? Was it the haunting Skull Nebula, the delicate hourglass of the Southern Ring, or the raw power of the antennae galaxies? Let us know in the comments below and keep looking up. The universe's greatest catalogue of mysteries is still being